Hi students, this is Chemistry 280. Today we are having lecture 2. In the lecture of today we are going to study the atomic theory, the periodic table, ionic and covalent bonds, nomenclature of inorganic compounds, and we are going to learn how to determine molar mass. Let's begin by the atomic theory. The first person who spoke about an atom properly was Democritus before Jesus Christ, and he considered that all the matter was made of atoms, small particles that were not were indivisible. But he said that between atoms there were empty spaces. We can say that he was very close to the actual idea of what an atom is. But the problem is that his theory was not accepted. During that time, Aristotle's theory was the one that everybody accepted. That he said, Aristotle said that everything was made of 4 elements: earth, wind, fire, and water. It was not until the 18th century when the chemistry began to be converted into more scientific, and Lavoisier in 1789 was the one who established the law of conservation of mass. He says that in a chemical reaction all the matter remains constant. It means that the mass of the reactant is equal to the mass of the product. In other words, matter cannot be created or destroyed, only transformed. The law of definite proportion that was established by Proust in 1799 established that a compound, when it is broken down into its constituent elements, the masses of the constituents will always have the same proportion. In other words, you remember that the water molecule is made of 2 atoms of hydrogen and 1 atom of oxygen. Let's see. Water is H2O. Then there is a rate that was constant between the number of atoms of hydrogen per the number of atoms of oxygen. Dalton took into account these 2 laws, this law and this law, and he established that each chemical element is composed of atoms of a single, unique type, though they cannot be altered or destroyed by chemical means. This is very important. And that they can combine to form more complex structure. What is the chemical compounds? Then hydrogen gas plus oxygen gas produces water gas. Then the atoms combine in certain proportion to produce more complex structures. Let's continue then to the following slide. Well, here what you are looking here is what we call Crookes tubes. They are at vacuum, they are empty, and they have two electrodes. One electrode here, another electrode here. When they established a difference of potential between these two electrodes, they observed a rate of light that was produced from one side to another. These were known as cathodic rays. But Thomson discovered that when a magnetic field was located between by the sides of the ray path, he observed that the ray was deviated to the positive charge. Then it gives us an idea that these particles were negative. He called these particles corpuscle. But after, the scientists agreed that the name was electron, and you know that the charge is negative. The model that Thomson proposed about the atom is known as plum pudding model. It was in 1909, in the 20th century. This model established that the whole atom was a positive mass, and in there you can observe the blue spots that represent the electrons in this positive mass. Well, he was not right. After that, immediately Rutherford, one of his students, produced or used a source of alpha particles that were positive, and these rays went through a very thin gold foil. If the atom were positive, of course these positive rays will go back, all of them. But what happened in the real life? Mostly passed without no problem at all, and only a few were rejected. Only a few. What does it mean? If the particles were positive and they can go through, then the atom was not a positive charge as a Thomson model. Most of the rays go through because the atom was or empty or was made of electrons. Then that you can see here. Then Rutherford proposed what we call planetarian model or planetary model, where he said that the nucleus was positive charge and only occupies a small space in the center of the atom, and the electrons were in orbits around this nucleus, as you can see here. Then this is the planetary model that was the Rutherford model. After certain period, Bohr and other scientists used the hydrogen atom and proposed a model. His model said he observed the radiations of the atom of hydrogen, and he said that these rays in the spectra represent transitions of the electron from one level of energy to a lower level, and then they release this energy, and the energy is related to the rays that we can observe in the spectrum of hydrogen. Well, he arrived to a model that was proved, but only for hydrogen, because he didn't consider that in other atoms than hydrogen there are more than one electron, and then he didn't consider the interactions between the electrons in the around the nucleus. Then his model exactly said that in the nucleus we have the protons that were positive, and around the nucleus in orbits that represent levels of energy were the electrons. Level 1, the inner one, and 2, 3, 4, 5, 6, 7 until 7. Every level, the higher the level, the more energy contains this level. Well, as the model of Bohr didn't explain other atoms than hydrogen, then two people, Heisenberg and de Broglie, working separate one from the other, and Redinger proposed that the atoms, the electrons in moving around the nucleus, have a dual behavior as wave and as photons. Then the electrons as the light have a dual behavior as photons or as wave. And they proposed the quantum chemistry, or that is a theory that explains the structure of the atom, how the electrons are distributed in different levels of energy around the nucleus. And they say that the orbits were not exact circular orbits. The orbits are the most probable space of the atom where we can find an electron. That's quantum chemistry, or also mechanical quantum in general. Here you can see a distribution that we are going to use to do the distribution of the electrons for every atom, that says that in level 1 we have orbital s. Orbital s only can have 2 electrons, but also we have orbital p and s in level 2. S continue having only 2 electrons. P can have 6 electrons. D can have 10 electrons, and F can have 14 electrons. For example, for an atom like carbon, as you can see here, you say carbon has 6 electrons because the atomic number is 6. Then it will be 1s2, 2 electrons in level 1 orbital s. Then the following one, 2s2, 2 electrons in level 2 orbital s. And then the 2 other electrons will be in 2p. Then 2 plus 2 plus 2 is equal to 6 electrons. That is an atomic number of carbon. You can represent it also the s orbital by a square and the electrons by arrows in opposite direction because it's the way they are spinning around the nucleus in order to have the least interaction possible. As they are both negative, they have repulsion interactions in between. Then in level 2, as you can see here, the 2 other electrons, and then pay attention. You don't begin pairing the electrons until you have at least 1 electron in every square of level 2p. For example, what is the difference between carbon and nitrogen? Nitrogen has 7 electrons. Then it will be 1 electron, 2 electrons, and 3 electrons. And oxygen that has 8 electrons is when you begin pairing the electrons. And so with fluorine, that you pair 2 of them, and neon, you have paired the 8 electrons, the 6 electrons, sorry. Then you can represent the electron distribution by using this diagram, and this is the notation you can use. Always you begin from here and then continue from here and then continue here and then here, and so is the order you are supposed to follow. In the periodic table you will observe 2 numbers. A small number that represents the atomic number, that is the number of protons, positive charges, the symbol of the element, and a big number that represents the atomic mass of the atom. In the atoms we have what we call isotopes. It means that for example, carbon has carbon 12, carbon 13, and carbon 14. What does it mean? That all of them contain 6 protons, but this has 6 neutrons, this 7 neutrons, and 8 neutrons in the nucleus. That is where are the protons and the neutrons. Neutrons are positive while neutrons are neutral. Then, if you want to determine the atomic mass that is in the periodic table, it is a decimal, while here you observe there are whole numbers. But what happened? All the atoms has not the same abundance. For example, for let's see this example. Neon 10 has an abundance of 90.92%. Neon 101 has an abundance of 0.26%, and neon 22 has an abundance of 8.82. What you do? You multiply the abundance by the atomic mass of the atom, and then you add this result by the multiplication of the abundance by the atomic mass of the other, and then you add the multiplication of the abundance times the atomic mass of the other, and you divide everything by 100 because you used percent, and you get a number. This number is, in this case, is 20.18. This is a number that you will observe in the periodic table as average atomic mass per one element. This exercise is very important. In one exercise that you can have is, for example, I will give you the data for one isotope. In this case, it's carbon 14. Well, you go to the atomic number. If you observe that the atomic number is 6, it means that you have 6 protons and 6 electrons, because one is positive, the other is negative, but the whole atom is neutral. That's why you have same number of protons than electrons. And then you subtract the atomic mass minus the atomic number, and you get 8. This is the number of neutrons. Then remember, the atomic mass gives you the number of protons that at the same time is the number of electrons. And neutrons can be determined by subtracting atomic mass minus atomic number. The first representation of a periodic table was made by Dmitri Mendeleev. What he did, he began ordering the atoms according with the atomic mass. But he observed that every certain number of atoms, the following one will have similar characteristics than the one that was before. And so here, and then he joined in the same column atoms with similar behavior. The modern periodic table is ordered according with the atomic number, not the atomic mass as did Mendeleev. Let me tell you that Mendeleev, during his time, he observed that there were spaces empty, that he left empty because he knew that there was an atom that was not discovered by that time, and he was pretty exact in his prediction. When the atom was discovered, the atom fixed exactly in these empty spaces that Mendeleev left. The modern periodic table is divided into, according with this zigzag line that you're observing here, you have non-metals to the right and metals to the left, and these ones that are in between are the metalloids, elements that has characteristic of metals and non-metals. The periodic table is divided in groups that have the letter A, 1A, 2A, 3A, 4A, 5A, 6A, 7A, and 8A. These columns or these groups with letter A are known as representative. Representative elements, and the ones in the block in the middle are the transition elements. Then in the periodic table, according with the order that we have there, that is according with the atomic number, not with the atomic mass, we get that we have with the letter A the representative elements, and in the middle with the letter B the transition elements. In the bottom we have lanthanides and actinides that we are not going to study. The groups has a specific name. For example, group 1A are the alkali metals. Group 2A are the alkaline earth metals. This block in between, as I told you, are the transition metals. This group that is here, that is 7A, are the halogens. And the last one, 8A, are the noble gases. In other hand, this row 1, 2, 3, the rows are known as periods, and this period represent what? In period 1 you have only one level of energy. In level 2, 2 levels of energy. In level 3, 3 levels of energy, and until the 7. Let's see the characteristic of metals and non-metals. Metals are shiny, non-metals are dull. Metals are hard or very hard, and non-metals are brittle. Metals are malleable. It means that they can take different forms. Non-metals are non-malleable. Metals are ductile. It means that you can make wire with them. Non-metals are non-ductile. Metals are good conductor of electricity and heat. Non-metals are bad conductors. Metals are all of them in the solid state except mercury. Non-metals can be in the 3 states. The density of the metal is always higher than non-metals. In between we have, as I told you, the metalloids. They have properties between metals and non-metals. So metalloids are semiconductors. They mean that the semiconductor means that they can carry an electrical charge under special conditions. Then that's why we can have computers, calculator, TV set the way we have right now because of the use of semiconductors. Atoms can have two behavior. They can lose electrons and make cations that are positive ions, or they can gain electrons and get anions that are negative ions. For example, lithium can lose electrons and get a positive charge, as fluorine can gain electron and can have a negative charge. Here in this table you can see the most probable charges for certain elements, representative elements. But what happened in the real life? That you have, for example, chlorine that is a non-metal with sodium that is a metal. When they join together, they make what we call an ionic compound. That is sodium chloride. Then the union of a metal with a non-metal produce an ionic compound. In a formula, you have the symbols of the elements, and the subscript indicates the number of atoms. In covalent compounds, we have always non-metal plus a non-metal. They share electrons. It's different as the behavior of the ionic compounds, where the metal releases electrons and the non-metal gains electrons. But in this case of the covalent compound, we have to use prefixes to indicate the number of atoms. For example, this one that you can see here is carbon monoxide. You use here mono because you have only one atom of oxygen, and as you can see, ends in "ide." But in the other case, carbon dioxide, because you have two atoms of oxygen. In the metals, always you put first the metal and then the non-metal. But we can have, in the first case, metal that has only one charge, like this one that you have here that belongs to group 1A or 2A, or for example aluminum that is in 3A. Also zinc and silver that are transition are in this case, because they always work with one charge. For elements with one charge, all what you have to do is to put the name of the metal as it is in the periodic table, and the non-metal will change the ending into "ide", as you can see, oxide, bromide, oxide, chloride. This is calcium oxide, potassium oxide, aluminum oxide, magnesium oxide. If you join sodium with bromide, you say sodium first because it's the metal, and then bromide second because it's a non-metal. Sodium is +1, but sulfur is -2. Then the 2 goes as subscript of sodium, and then the 1 that is in sodium goes to sulfide. Nitride, well, you have a -3, that's why you have to put 3 sodium per 1 nitride. Aluminum is 3 positive, then you need 3 negative bromine, because bromine is -1. In the case of this, you have to put 2 aluminum because of a charge of aluminum is interchanged with aluminum, and then sulfur get the 3 of the aluminum. In other words, you have aluminum plus 3, sulfur negative 2. This 2 goes here and this goes here. Then it is aluminum 2, sulfur 3. That's the formula for this compound. In the case of aluminum and nitrogen that both have negative or positive 3, you just write Al and because you cancel out the 3 with the 3. Then look at this. For the metals that have only one charge, you write the name of the metal as in the periodic table, and the non-metal changes into ide, the ending. But also there is a type of metal like the transition that works with more than one type of atom. What you have to do in this case? Well, you write the name of the metal and then into parentheses you put the charge. If it is 2 plus, you write with the Roman number a 2 or a 3 or just a 1 according with the charge of the metal. That's why you put chromium 2, chromium 3, iron 2, iron 3, and so on. But also, you can have compounds where the anion is polyatomic. In this case, you don't have to memorize it. You can bring this table, you recognize the polyatomic ion, and then you have here the name. For example, sodium carbonate. Sodium works with +1 and carbonate with -2, as you can see there. That's why this 2 comes here and this one goes outside, but you don't write it. This is for polyatomic ions. The last thing in the class of today is to determine the atomic mass. What is this? The mass in gram of 1 mole of the compound. We are going to see what is a mole. Remember, that is the way we can measure amount of substance. What you do? You use the atomic mass of the element. These are the atomic mass from the periodic table. And you multiply by the subscript that indicates the number of atoms. And then you add. This is the mass of 1 mole of water, 18.0, and so on. In this case, this 2 is affecting the 4 and the 1. That's why you have 2 nitrogen and 8 hydrogen. Well, that's all for today. Let's continue in the following class. Thank you.